So
Okay.
is it recording or not?
Yeah, it says being
Yeah.
recorded.
So so let's welcome you all in the second Gauge Gravity by the Ghat seminar. And today we have Heng-Yu Chen from National Taiwan University. And Heng-Yu has been he did his PhD in Cambridge. And thereafter, he was a postdoc at Wisconsin Madison, followed by a postdoc at Cincinnati. And after that, he joined in NTU as a faculty. And his research interests are superstring theory, supersymmetric gauge theories, integrable system, and mathematical physics. So today he will be talking to us about exploring complex shadows and geometries through holography. Now, for the questions, basically, usually we have the questions after the talk, but if in case there are any urgent questions, we can accommodate in between the talk. So, Heng-Yu, up to you now.
Okay, so thanks, organizer, for the invitation. And yeah, first I would like to apologize that yesterday was a slightly food poisoning issue that I had to postpone the talk to today. And also that today is actually a public holiday in Taiwan, so I'm doing this at home. So if you hear some screaming, no worry, that those are my cats. So don't worry, everything is fine. Okay, so very happy to share this series of work that which I've done in collaboration with friends in Japan, Yasuaki Hikida and Yusuke Taki and Takahiro Uetoko, which we basically did in collaboration over the past couple of years. So the general idea, yeah, is actually trying to explore, well, path integral that which we usually involve, for example, a certain parameter that which we know as they can be, well, when we consider both the path integral in quantum field theory, but also path integral involving the gravity. Now we involve certain physical parameters. Now normally we would take those physical parameters to be kind of real value. But a lot of time, especially recently, like for example, in the context of holography, it turns out that it's quite interesting that when we actually, for example, promote some of those parameters from real to complex value, those can be, for example, like the fugacity parameter in the context of supersymmetric indices. Now, or it could be like what we're going to talk about in today's talk, that, for example, like a certain coordinates that in the gravitational path integral into complex value, that we will usually discover there are interesting additional saddle points that when we are evaluating those path integral in some appropriate weak coupling value. And those saddle points turns out to be of a lot of interest. For example, that one of the really striking result over the past 10 years ago, or 10 years or so, was that when we, for example, trying to matching the supersymmetric indices for the superconformal field theory, and with the counting of a black hole entropy in the asymptotic ADS black hole, that is actually almost necessary that for us to actually promote some of those parameter in the superconformal indices, so to speak, into complex value, and then you can discover the correct saddle point that which reproduce the black hole entropy. So it's a useful thing, and it's actually an interesting direction to study in general. But often that when we try to naively, right, for example, taking our those parameters into complex value, we also kind of encounter some interesting puzzles. And basically, it's today's talk's topic that we will try to see that how having the tool of holography. So the basic thing here is that we are going to assume in the kind of holographic correspondence that how the holography can actually allow us to, for example, resolve some of the kind of puzzles that we encounter when we kind of naively basically promote, for example, in our case, we'll be mostly looking at the gravitational path integral, and when we promote the coordinate into complex value, then we will encounter some puzzle, and how the holography, basically the dual CFT, that will actually allow us to resolve some of the puzzles that arises in this context. Okay, so that was a general kind of one line kind of summary that with what's going to happen next. Okay, so so that's kind of like first point I will cover, and then basically a classic example, like when we're trying to kind of complexify a metric, which later we're going to enter the gravitational path integral, is actually given by a nice paper by Witten a few years ago. Now, so the starting points that we can look at, for example, trying to just complexify a d+1 dimensional sphere. Now, of course, we all know that, for example, this metric in the front is actually, if we just simply have a d by d theta here, then we are just having a kind of d+1 dimensional sphere. But now, if we actually allow theta itself being a function of some parameter u, and the simplest case that when u is just equal to theta, and if we restrict it on the real line, then we have our usual sphere. But however, if we now actually allow for u to become purely imaginary, that so for example now, and actually let the u to go from plus and minus infinity, then now the metric actually become something like a Lorentz d+1 dimensional Lorentz de Sitter space. And so these two extreme cases, and in general, if we allow for u to be a complex parameter and let the u kind of traverse in the kind of complex u plane, and of course you can have theta of a u is and a complicated function of a u, then it allows for different kind of possibility of promoting the metric into a complex value. And so normally when we're trying to evaluate the gravitational path integral, what we normally do is that we will substitute this kind of metric into our path integral and actually promoting kind of various kind of fields into just like when we perform path integral, that it becomes something you will evaluate it over with. And so naively, we want to actually kind of summing over all this possibility. But they actually give quite a lot of puzzle coming from this, just naively doing this. So, for example, the reason why we take this example, of course, it was also because it's of interest of studying the kind of evolution of a universe. So just now so for example, if we started with something like a kind of d+1 dimensional sphere, and if we assume, for example, our universe actually started from a bubble of nothing, so normally we want to, for example, now let this metric actually collapse, and then this corresponds to setting, for example, cos theta squared to be 0. And there are various kind of possibility that for this to happen, that each of them you can actually view this as for example, some kind of initial condition that which labeled by different value of n, and then you kind of let the universe evolves, and this basically correspond to, for example, in the theta u plane, that then you let the u, for example, starting to take a complex value, and theta basically now it was started from real axis. You have this, for example, it started with certain value of the n, and then you started with some bubble, and starting from a real axis, and then move into the complex, purely imaginary axis that we recover, for example, our d+ dimensional Lorentzian space, that which are going to be doing our inflation and so on. So, but otherwise, this seems to be reasonable. But then at the same time, now all this, infinite possible initial condition that in terms of evaluating the gravitational path integral, there's no particular way to kind of pick any one of them as a preferred condition, since they kind of give exactly the same kind of bubble of nothing initial starting points. So, okay, so what can we say about this situation? And why is this kind of giving us a puzzle? Is that so? But more precisely, that what's happening here is that in terms of evaluating the complex action associated with each of those metrics, once you kind of plug in those things into the Einstein-Hilbert action, then we can actually evaluate in this. So these things now actually, the Anshar action basically now consists of real and the imaginary parts. And what we later see in an explicit example, we're going to engineer this situation in a kind of more explicit setting. Now we'll see that actually the real part here is actually for each value of the n, that was the n label in a different initial condition. It's actually going to be goes like the following form. The S is the case for the precise for n equal to 0, and this is the kind of de Sitter entropies, the space for the entropy for the de Sitter space, and this implies that we can actually kind of increase the amplitude, and meaning that when n gets larger and larger, this actually becomes kind of dominating contribution in our path integral over all the other kind of saddle points. So, and this actually gives some kind of puzzles that if we actually want to, for example, kind of reconcile with the original proposal by Hartle and Hawking, which actually, it turns out that for all this infinite possibility, that we could actually only have the most natural cases we can have, which is basically like the case of n equal to 0 or -1, or in other words, that we actually only have a simple kind of S2, rather than, for example, all this higher value of n that is actually kind of correspond to kind of multiple winding of the over the sphere. So yeah, so how do we kind of resolve this really? I mean, and this is actually quite kind of one of the very simple things that we started with with a very simple metric, and we're just naively kind of moving the coordinate of the real axis. Then we encounter this kind of rather confusing and likely in this case kind of overcounting situation in the gravitational path integral. And basically in today's talk, we're going to see that how in a situation now with a holography dual that we may be able to resolve some of these puzzles. But it worth mentioning that purely, you can also view this purely as a kind of geometric problem that, and then, well, you can ask whether like a mathematician that actually provided some geometric criteria that which allow us to say what are the kind of allowable complexification of a metric. And it turns out that what, and I think that was one of the motivation that Witten originally wrote this paper, was that trying to bring this result from the mathematician Konsovich and Siegel, that at the time they were considering the metric with a definite signature. But now if you want to kind of start it from a real d-dimensional metric, and they want to kind of promote it into a complex value, and the kind of allowed criteria for this kind of complexification is essentially boils down to something what physicists will actually write down ourselves as well. Because what it proposed was that now suppose given on this kind of manifold, if you construct all the possible differential form that which like for with a dimension less the actual physical dimension. And you consider the following quantity IQ here, which is basically what we will write down as an action for this differential form, that if we were trying to later promote it and study dynamic, etc. And the allowable metric here is just simply by demanding that this basically this integrand inside this action to be basically positive, but the real part here to be kind of positive. And in other words, from physicists kind of terminology, this is actually just demanding the kind of positive kinetic term. We will want, for example, of course, you can also view this as from kind of perspective of path integral, that once you substitute this, and of course, for physicists, you will start usually with some Lorentzian signature instead. But actually evaluating path integral, we're often trying to perform the weak rotation, and basically make it purely Euclidean. And then all these things are coming from, for example, demanding the the action itself to be actually convergent. That when you kind of go into the Euclidean signature. So that's kind of useful, and in principle, we could also actually test some of the complexification of the space-time metric using this kind of criteria. But of course, in many of the physically interesting cases, that especially when we consider higher dimensional gravity or manifold become more and more complicated, it's much harder to actually check this thing explicitly, to construct all the possible, for example, all this differential form, and actually trying to ensure that, right, when you evaluating these things, that f would take a value over the complex coordinate, and to actually ensure that this is really kind of positive everywhere. So this is actually nice condition, but much harder to kind of check explicitly. So it's another kind of motivation for this series of work we're doing, that trying to use holography as a tool that to kind of provide a different take on this situation. Okay, so that's a general idea. But any question or comment so far about where we are going? I'm going a bit slow in the beginning, but I'm going to start talking about more details. Yeah, but feel free to interrupt me anytime. Okay. Right. Okay. So as I was mentioned to Gaurav earlier, that this is strictly speaking, this series of work, strictly speaking, is a kind of like a spin-off from the slightly different direction that Hikida and I were started with. At the time, we were trying to cook up an explicit example of a three-dimensional calculable example of a three-dimensional de Sitter CFT correspondence. And this, of course, relies heavily on the fact that in this three-dimensional setting, that the holographic dual CFT that we are
So
have a
Heng-Yu?
very yes, hi.
So there is
Yes.
a question by Sayantan.
Okay.
He
Yeah,
wants to
okay,
ask
please.
something.
Yeah, okay, please.
Yeah, sir, could you just go back to the previous slide where you define the Seagull action that can do? Yeah.
This one, yeah, okay.
Yeah. So I am actually getting little confused about the matrix. So if I understand correctly, if Q equals to 2, it's the just Yang-Mills equation, right? I mean, F mu nu, and with the contracted, right? 1/4 of this. It would just be the Yang-Mills equation if I take Q equals to 2.
Yeah. So that's important to have a definite signature. So they are not dealing with Lorentzian. So yes, for Yang-Mills, you have a E squared minus B squared, as we know. And that in general may not necessarily be positive. Yes.
So the complex metric G means that whatever, say the Lorentzian metric, we are Euclideanizing with the one component as a I, right? I mean, say the 0 component, what the signature was minus, we are complexifying that. So is it fair to say that it is not like a complex metric, it's like a metric with only 0 element as a complex, right? Complex, and rest of them are just diagonal element. Is it fair to say? So I'm just trying to figure it out, the metric G in the real Lorentzian case. So how is it related to Minkowski?
So basically, in this case, yeah, they are not dealing with a Minkowski case. Yeah, so they are basically only dealing with it. So Minkowski is a case that that with a one signature is a minus, right? It's different. So they are using that's why I was starting earlier saying that all the metric with a definite metric that in a kind of plus signature, there's no minus one.
Yes.
Yeah.
So
yeah. So
okay.
So then you complexify. So for example, like the sphere, that's one example that we could use this criteria to check, but not the Minkowski space-time, for example.
I see. So just for a clarification, so if from this complex metric G, if we go to the real one and say we take Q equals to 2, it would be just a Yang-Mills equation, right? I mean that 1/4 term. Okay, sure. Thank you very much.
That's right.
Thank you.
That's right. Yeah. So initially we were also very confused by this condition. Then yes, because the most natural objection of this precisely is that when you have a Minkowski space-time, then you have E squared minus B squared. Then how can this always be positive? And yeah, but that's the case that
because if it is Young-Mills, then the second one follows obviously. The real part of it is greater than 0. It just means the mass energy density is positive, just like even the electromagnetism. Yes.
That's right. Yeah. Okay. Good. Yeah. Right. Good. But okay, so we basically have a slightly different take on this. So right. So basically, we would So cut to the chase is that a couple of years ago we started out talking about this by performing the kind of analytic continuation of the Chen-Simon description of the three-dimensional Einstein gravity. So, and then trying to basically leverage this to describe the gravity in the de Sitter space, asymptotically de Sitter spacetime. So, but let's just quickly review what our starting point. So we started with basically consider the kind of Einstein gravity with a negative cosmological constant in 3 dimensions. And so writing it out in the Chen-Simon formulation, that we are essentially considering a Chen-Simon gauge theory, 2 copies of them with a gauge group like SL2R. And if we relate the Chen-Simon level with the gravitational constant in the basically in the 3-dimensional gravity, and also the typical kind of scale size in the following way, then what we can do here is that by parametrizing the gauge field of the 2 copy of Chen-Simon theory in the following form, that we could basically map the equation of motion of the Chen-Simon theory. Well, actually, it's better to say the other way. We can map the Einstein equation of motion in 3-dimensional gravity into the Chen-Simon's equation of motion. And here in the middle, just labeling out the commutation relation among all these generators that, of the SL2R algebra entering the parametrization of the gauge field. So we can basically say A plus and minus here, then it's going to label the different different gravity solution that in the resultant kind of Einstein gravity, and the x plus minus here will appear as the coordinate in the kind of resultant metrics. So as a simplest example, that for the ADS3 BTZ black hole, then this is a kind of profile we are actually looking at for the A plus and minus, and here the curly LADS is just a combination of the ADS metric and the horizon, the radius. So by substituting or basically taking the inner product of those gauge field, we could actually recover the metric of the ADS3 BTZ black hole in the following form, and or more precisely, that is a kind of slightly change our parameter from the radial coordinate into this kind of cosh of the actually this cosh of the rho fields, which will enter the metric. So this is a kind of like a simplest case. So, and actually, if we try to avoid the conical singularity that which will appear at the horizon, then we actually need to make this following periodic identification that whose periods is actually inversely proportional to the horizon, basically the horizon radius. But this is actually give us a much natural way to, since all these are from the perspective of gauge theory, that they cannot be, well, how should I put it? We cannot really label different kind of physical configuration based on the gauge field, but rather we need to have a kind of gauge invariant quantity. And having this kind of like periodic identification or compactification of time coordinate, this actually gives us a very natural way to actually label different gauge invariant configuration, that by looking at instead of Wilson loop, that we can define based on basically each of those gauge field. We can actually define the Wilson loop here, and we can further decompose this in terms of its kind of monodromy matrices. So in other words, that this Wilson loop are invariant under those kind of unphysical gauge transformation and so on. But however, for those Wilson loop now, we can still allow for the kind of additional large gauge transformation along the S1 along the time direction, and so that will actually shift it the monodromy matrix monodromy value into this kind of integer unit. And later we'll see that in the case of de Sitter, of course, also in the case of ADS, that this actually generate very different space-time metric, and the space-time action are also very different. Okay, so this is a slight review of the ADS3 starting case. And so what we did was very simple in our paper was, in my paper was Hikida, and also following some of the earlier work by Nishioka, Takahiro as well. Right, so we basically, or another motivation we could see this is that we were actually trying to study the not only, so just now we're looking at Chen-Simon theory with the only real gauge group. So more precisely speaking, what we are doing in doing this kind of analytic continuation is actually trying to promote the gauge group into this SL2C instead, into a complex gauge group. So what we are really doing here is that then in doing this kind of analytic continuation of the, for example, in a kind of very natural, of course, you can also view these things from the embedding space metric that, trying to change all the ADS radius to the de Sitter radius in a kind of obvious way and perform this kind of continuation. But what we are really doing is that we are kind of looking the kind of purely imaginary part of this kind of more general kind of complex Chen-Simon gauge group, and just not the ADS if you want. It's kind of like the real part of it. And in doing so, then we actually have to impose a slightly different kind of conjugation condition on various generator that entering the gauge field. So there's slightly some technicality here. But all this parameterization are pretty much directly follow from the kind of ADS cases. So this allows us to, for example, to define I wouldn't necessarily call this a black hole, because strictly speaking, the horizon we are entering here is not a event horizon, but rather it's actually kind of cosmic horizon. So, but in any cases, we kind of analytically continue the ADS BTAZ black hole that we encountered earlier, and into this kind of de Sitter analog. And this is a metric that we kind of obtaining by this kind of change of parameter or analytic continuations. And we could, so these are the kind of some redefinition of the parameter that needed over here. So, and so this is more explicit, writing down in terms of the radial coordinate and also the horizon precisely at where the time component kind of vanishes. So again, now here to actually avoid the singularity, the conical singularity at the horizon, that we have the same kind of periodic identification, and that allow us again to define this the Wilson loop that by having those just basically wrapping the gauge field along it, and they label kind of different physical inequivalent configuration. So, and a couple of things we can say about it, of course, first is that we could, for example, plug this metric into the Einstein-Hilbert action and, evaluating its value, and that give you the corresponding entropy here. And, but what's happening here is that once we perform the large gauge transformation, like what we mentioned in the ADS cases, then is that now the metric, of course, changes. So this is the explicit writing out all this large gauge transformation, now we're kind of shifting the time components, and now the metric take the following form, which you know, you have a different metric for each value of the n here. And as a result, once you plug into the Einstein-Hilbert action, then of course you also give this very different value in front, and is actually proportional to n plus 1. So this is kind of like the explicit realization of the situation we mentioned earlier, that, for example, now if you want like having a different well, just by performing this kind of gauge transformation, now you will actually generate the saddle. So because each of them will contribute to exponential minus of the s here, and then we actually generate saddle point, but of different values over here. But otherwise, there's no there's no from the perspective of path integral. There's just a large gauge transformation, and from the value from the perspective of Chen-Simon, most precisely from the Chen-Simon path integral, there's no reason to actually bias against any value of the n, and naively you just have to summing over all of them, and but this may lead to the overcounting, for example, that we mentioned earlier, if we were trying to recover the result by Hawking and Hartle, and or just generally, there's just so many possibilities here that they seem to be quite confusing. Okay, so that's the status. That's kind of like the puzzle that we, and of course you can view this. So it's in the line in this line of logic, you can view this as that it's a attempt that, for example, if you naively complexify, like starting from say your real ADS metric, that you start into going from to the de Sitter spaces by taking the parameter, for example, the ADS metric to the complex value, but also coordinates that to the complex value. But then in doing so, that you have this issue kind of arising here. Okay, so that's the issue. And that's where the holography kind of come in to help us, that to kind of distinguish all these possible saddle points, or at least figure out which one we should actually be keeping here. So this is kind of follow from kind of the earlier work, our explicit work on the de Sitter three-dimensional de Sitter CFT correspondence that I did with Hikida. So in this case, it's a dual field theory that following a chain law triality. I'm not claiming. This is something I should make a disclaimer here, that I'm not saying the pure alluvial theory here is actually describing directly describing the as a boundary theory of the de Sitter gravity, but actually we can use this crutch to actually compute the correlation function that we are interested in. But okay, but our starting point here then would be looking at this kind of regularized action for the alluvial theory. And so here that this is the usual alluvial action, and now here we are going to have some boundary, or more precisely some puncture on the worldsheet, that where we're going to insert various vertex operator, and we could also have some background charge term which coupled to the worldsheet curvature. So the vertex operator take the usual form of exponential of alluvial field, and they are only labeled by the different kind of twist or scaling dimension, if you want, that which we can parameterize in terms of this parameter alpha, and also background charge. And they themselves in turn are related to the central charge of the alluvial theory, and also the coupling constant in the following form. So the nice thing about it is that we could actually, first we could make the direct connection that of the central charge with the the gravitational constants that in this explicit example of a 3D de Sitter CFT. And but what's really nice about it in in making this correspondence here is that, so basically the classical gravity, right, the problem we are trying to address just now, is precisely mapped to the large central charge limit of the dual CFT. And the large central charge limit in 2 dimensions play an important role that allow us to, for example, especially when we're looking at a higher point correlation function that, for example, 4-point, that allows to, for example, simplify the Liouville conformal block into just a purely the global conformal block. They allow for certain truncation, but also allow for the correlation function that in this setting to be also evaluated in terms of the saddle points. Saddle point approximation, my apology. So specifically, in our case, that after this relation between the gravitational constant and also the Liouville charge, the Liouville coupling constant, then we can obtain the following relation between the B and the central charge. So the leading term here, because we now actually going to the complex value, it's actually purely imaginary. But the subleading term, and more precisely, the subleading term here is real, and its sign is going to play the kind of important role when we try to perform the analytic continuation of the Liouville correlation function later. So just keep this in mind. But before we do that, we could also just directly take all this limit and perform a basically rescaling of a various fields in the Liouville series, and trying to evaluate the correlation function using the saddle point approximation. So more precisely, we are interested in this de Sitter analog of a BTZ black hole, and via this holography, this actually corresponds to looking at the 2-point correlation function in the Liouville series, and making it very, very heavy. Yeah, so roughly speaking, this is like inserting some kind of cosmic string configuration. So by this scaling, so V alpha, VZ1, VZ2 alpha, now they are basically a very heavy operator. And what we can see here is that by kind of by performing this rescaling, then this the presence of this operator insertion, actually they become a kind of delta function sources. And this actually in turn modified the Liouville equation of motion that by providing these additional sources here, or more precisely that the eta here, which is controlled by the basically telling you the scaling dimension carried by the 2 vertex operator insertion, is giving you it's labeling the kind of conical deficit on the CFT worldsheet metric. So this basically changed the equation of motion. And what we see here is the following, that so just now, for example, we were interested in those infinite number of saddle points, or we're trying to, well, at least if holography is true, that we should at least see that the presence of those kind of infinite saddle points that we encounter on the gravity side just now. And here, this appears very naturally, right? Because from this equation of motion, that we can see that suppose if we find a classical solution, phi of C0, which I call here, satisfy this Liouville equation of motion, we can see that there's actually infinite copy of them just by this constant shift 2 pi n, since the derivative just annihilate all this constant shift, and this term here, actually if I miss an I here, there should be an I here. That doesn't change the equation of motion here, and the delta, of course, doesn't care. But however, we can evaluate this, the corresponding, we can substitute basically this infinite number of the solution into the alluvial action. And we see that basically now this kind of back reacted. Another way you can view this inclusion of this vertex operator, kind of this back reacted alluvial action now actually pick out this overall factor of n plus half here. So this is if you want, this is kind of like a manifestation that if you compare with the what we saw earlier in the gravity side, there's also overall factor of n or 2n plus 1, right? In the gravity side, when we evaluate the corresponding entropy of a different copies of a large gauge transformed BTZ black hole. So we see kind of the same puzzle. So this is a kind of manifestation. Now we see the same puzzle that builds on both on the gravity and also on the kind of CFT side. So then how do we resolve this issue? Well, happily, what's happening here is that we only did a one way of it, right? Just now we were evaluating this 2-point function via this saddle point approximation. But happily for 2-point function, that there's a much more, well, we know the exact answer, and it's thanks to the work by the DOZZ. Well, ZZ stand for the two Zamolodchikov, and the D and O are the Dong, and I can't remember what O stand for somebody. But there's a nice paper like 30 years ago that we could actually compute like 2-point function exactly, in the sense that we actually know the overall coefficient as well, right? Not just because this part, the Z dependent, are just fixed by the conformal symmetry very simply. And what we have to do here in order to bring this into the same kind of regime that we are interested is actually trying to perform the analytic continuation of this complicated combination involving the gamma function with appropriate parameter value. Or in other words, we have to perform based on this particular both the in this particular B here, and with the correct sign of the real parts. And in doing so, happily this work was actually also done by Hollow, Mose, and Witten, right after, well, actually 15 years ago, even before Witten's original, more recent paper. And it's the following form, that this is basically analytic continuation. So it involves a few pieces here. And so the second part here, because at the order we are dealing with, the 1 over b squared here, just at the leading order, is purely imaginary. So the exponential piece is just giving you a purely imaginary term, and so are all these leading pieces that are just purely faces, really. And the only non-trivial term is what's inside this round bracket here now, because b at the leading order is purely imaginary. So actually this is a real value. The two terms here are real value. And that precisely corresponds to actually the plus basically n equal to 0 and the minus saddle that which will need it to actually recover the Hartle and Hawking answer. So in other words, in order for the two basically purely from the CFT, that we should really just keep out of all the possibility of all the solution, like just now we wrote down, we should only keep the n equal to 0 and minus 1. And then this very naturally allow us to actually recover precisely what we encounter on the gravity side. Or in other words, we can actually use this to actually pick up the correct saddle from the gravity side. So this is an example that how the holography actually help us to resolve the issue that we in terms of when we perform the complexification of the gravitational path integral.
Heng-Yu, I have a question.
Yes. Yes.
So what do you
Okay,
mean
good.
by picking up the correct saddle using the holography? So usually, if I understand, usually when we are doing the path integral, there are multiple
Right.
complex saddle might be there. Now, which one of
Right.
them is giving a more dominant contribution, like or
Right.
becoming relevant in the calculation?
Right.
This Picard-Lipschitz, which tells basically how to figure out. So,
Mm-hmm.
is it possible to figure it out using holography also?
Yeah, if the correlate, yeah. So here we are relying the fact that the 2-point function we know exactly. So I guess the data is more like this. Yeah, sorry, I should phrase it a bit better. So holography, naively just one saddle point, like this part is kind of manifestation now. Okay, whatever you saw as a difficulty on the gravity side, you saw it on the field theory side.
Mm-hmm.
Right, so you basically have this n here represent the infinite, right, infinite the large gauge transformation that you had earlier. So again, you had no way to throw away any of them, right? So naively, you would just if you were put it this way, if you were trying to evaluate the path integral for the Liouville field theory, right, and for this 2-point function, then you would just have to sum over all of them. So there was
Yes.
there's a overcounting as well, because what you realize that is, well, actually that's an artifact of only doing this leading semi-classical computation. And here, happily, we actually know the exact answer. That just from the Zamolodchikov's work.
Yes.
And in order to reconcile with this full quantum answer, you actually have to. You can only have a 2 of the, out of the infinite possibilities here.
I see.
So that's the status here.
Oh, very interesting.
Yeah. So this is something. Yeah. So basically, when we give a talk this elsewhere, then yeah. So basically, the same game. Yeah. Actually, I'm taking a slightly more. I may not be able to cover all the slices, but I really want to just talk about the interesting things that.
Okay.
So for example, one could also try to do these things for the higher spin theory as well. For example, we actually in our earlier paper, so actually a lot of those work was actually thanks to the Gopakuma and the Gabardillo. They did a lot of those things for the ADS higher spin cases as well. So we could also perform this kind of analytic continuation for the become kind of de Sitter higher spin field theory. And but yeah, so you can also ask the question if there's a similar puzzle on the gravity side, and whether you can resolve on the field theory side. So here, then this it basically kind of hinge on how much you really know for all this the W3 and all this other W algebra related CFT as well. Basically, availability of correlation, exact correlation function in those contexts. If so, then you could actually play kind of similar game in this context as well. Yeah.
I see.
Yeah. So actually, so we also did the case. So this is a part of kind of confirm. Just I will send the slide to you later if you need
Okay.
it. But right. So this is just another thing that when you evaluate the action and this all work, that's all great. So at the 3-point function, we could also ask the same. There's similar kind of question that we could play with, kind of in a slightly reverse direction. So DOZZ also had this is kind of even more non-trivial, that they have the exact expression for the OPE coefficient when you're dealing with the 3-point function. So this is the form, and the gamma here, well, actually this gamma B here is the upsilon function, which you can look at the definition there. So we could also ask the question now. So for example, if we were performing taking all the 3 operator to be very heavy, or in other words, they carry the large scaling dimension and so on, and what can we say about the corresponding gravitational configurations? So right. So roughly speaking, in this analysis, we can divide in the scaling dimension into two possible cases. That one of them is actually that when all this epsilon 1, 2, 3, that parameterized scaling dimension is some greater than 1, and the other is actually less than 1, obviously. And but more important is that all of them also have to satisfy this kind of constraint to make sure the 3-point function is well defined. So okay, so then the question is that, which cases is actually going to dominating your gravitational path integral, right? If they have each of them correspond to different kind of gravitational dual, and then the question then is that what kind of metric you have there, and the same thing you can, because just a general picture here is that we expected all this heavy operator, just purely from the experience ADS CFT, that when you have a heavy CFT operator inserted or with a large scaling dimension and so on, then they will correspond to some kind of back reaction on the gravity side, and then which will deform your original, for example, de Sitter metric or ADS metric and whatnot. And then the general kind of question we are asking here is that then, for example, can CFT, since in this case we know a lot of CFT data that allow us to, because in general on the gravity side it's much harder to construct the corresponding metric and so on, but at least can we say something about from the CFT that what kind of topological data are and so on. So for the case of 3-point function, in this analysis we can do the same, and because now we have this exact correlation function and perform the same kind of analytic continuation. For the first case, this is what we have, and the expression look very long, but all we need to know is that 1 over b is purely imaginary, so therefore exponent and everything else is real. And so this just gives you a pure phase. And as a result of this, that when you evaluate its norm, that which basically would correspond to the value of the gravitational kind of path integral, it's going to goes off order 1 here in the large C limit, in the kind of weak gravity limit. And this has obvious interpretation, actually, because each of those ni, roughly speaking, is going to map to the conical deficit, and or basically telling you the conical deficit angle more precisely. And it just can't cook up a geometry that which 3 of them summing over greater than pi on a 2-dimensional sphere, that which embedded inside your 3-dimensional geometry. But on the other hand, for the other cases, what we see here is that then again, all these terms actually give you just a pure phase vector. But non-trivial part is this guy. Now we could actually have so this whole factor, just now, this whole factor now actually give you a actually of order C contribution, and C here is very, very large when you actually evaluate it. So again, now here we see there are only 2 saddles that are labeled by this, but each of those saddles actually now give you this kind of overall contribution proportional to 1 minus epsilon, and here this is actually less than 1. And so the natural interpretation of the kind of corresponding metric is actually correspond to the following form, which actually, to our surprises at the time, that the explicit metric, so the explicit metric of this S3 with a 3 conical defect, you might think this is something, kind of something you should actually have much longer before. It was actually only discovered like 25 years ago by another 2 Japanese gentlemen that what the explicit metric actually look like. And what we can do is that, just to actually additional confirmation, what we did in our paper was that on CFT we evaluate this piece. On the gravity side, we literally just kind of plug this metric into the 3-dimensional Einstein gravity and matching all this parameter epsilon I using their metric. And they just basically show the match. It's basically corresponding volume of this this object. So that give a kind of very natural interpretation of what the metric should be. But I guess a more general story here probably would be that if you actually, we did a couple other interesting cases at the level of 4 point. Of course, they're starting to have a more interesting result that you may have to take some special limit, for example, like heavy light line, or like for example, actually all of them are heavy, then would be a limit that is much difficult for the 4-point function, but you may have to take other limit and leverage what you know exactly about the 4-point function. And happily, like in the for all this WNCFT, that there are example that is actually no expression know exactly as well. So one could play this game and then try to find out what's the kind of gravitational interpretation now when some of those things become heavy as well. So that's something like we did in our paper, like in a series of paper a couple of years ago. That, I mean, we of course did more than this, but we kind of highlight the two salient example that we did there. But any questions so far? Yeah, I mean, I of course swept a lot of details, but I hope to convince you that the how should I put it? Like in terms of starting from a real ADS metric complexified to de Sitter, they are puzzles, but then holography actually tell us something about how to resolve those puzzles and what the metric should be.
No, I don't have any question as of now.
Okay, good. Yeah, because I can't quite just sharing the screen. I can't quite see the audience. Okay.
Yeah.
Okay, so let me change the gear a little. Can I have another 10-15 minutes? I mean, I know I'm going a bit slower. Is that okay?
Yeah. Sure.
Yeah. Okay. So actually, on the ADS, just to make the distinction for ADS, actually that's interesting itself. So if we perform exactly the same thing on the exact 2-point function, Liouville 2-point function, now it's because of the sign of the real part kind of opposite. So we kind of the gamma, well, essentially it's just a fancy version of performing analytic condition of gamma function, really. So now this factor actually going to the denominator is the numerator. So now if you further expand this denominator, now you actually have this kind of infinite sum. So you actually, in the ADS, this is actually somewhat unsatisfactory, to be honest. I mean, I'm almost like telling you about the caveat of our result, that somehow in de Sitter, that we could figure this out pretty satisfactory, then matching with a Gibbons-Hawking result. But for the ADS, we still have this, in a way it's kind of consistent, but it's somehow unsatisfactory. That yes, we also have this, just starting from Chen-Simon, we have all this Wilson loop, then there's an infinite number of equivalent configuration. And on the CFT, even after this machinery, that we actually again have this kind of infinite saddle point that labeled by all this value n, and we see this in the exact 2-point correlation function. So yeah, this gives us somewhat difficulty in terms of resolving all these saddles as well. So what did we do? So we were trying to play a little bit of game, like in the case of ADS3, and that's kind of bring us to another direction later. That in the kind of more, how should I put it, more cavalier way, I would say this is a slightly exploratory direction now. When we were, trying to start doing this via the mini universe, that's another topic that I'm going to talk about a little bit. But okay. But the issue is roughly like this. So, for example, if we were trying to do the same, complexification that, instead of from de Sitter, but going from de Sitter to the sphere and then to the Lorentzian de Sitter cases. If we were trying to do the same thing for the ADS cases, Then we started with say complexification of a ADS3 metric that, and we performed the same kind of reparametrization and so on. So we want to study a cases of interpolating from Euclidean ADS3 to Lorentzian ADS3. So that corresponds to basically real value, imaginary value, so to speak. And so if we trying to construct some kind of contour that in the theta plane, then parameterized by the U. So yes, so this basically will give you the Euclidean ADS3 when you approach to 0. But however, that it actually kind of like become kind of multiple wrapping that in some kind of intermediate region that when 0. Sorry, actually I got it wrong. You actually approach to the Euclidean ADS3 when you going far off. But these things actually become kind of multiple wrapping of the S3 over this imaginary 3-sphere that well, basically you have in other words, you are basically looking at some kind of Chen-Simon theory that with a gauge field describing a multiple wrapping of the Chen-Simon gauge Chen-Simon field over the imaginary 3-sphere, and those are actually labeled by basically the homotopic group pi3, and they are given by this integer n. And this is precisely corresponds to this integer here. So, and we can be more explicit about what the difficulty is here. So is that what we are doing is that we're starting with the asymptotic geometry at Euclidean ADS3 that correspond to kind of late time. And suppose if we were trying to interpret this to Lorentzian ADS3, naively you might think this is just kind of easy and obvious, that just to change one of the the embedding coordinate to purely imaginary value. But the issue here is that then, so actually the Lorentzian ADS3 has a trivial bulk, that trivial bulk winding number and the infinite value. So you cannot even define this kind of large gauge transformation that we encountered earlier. But instead, that if we actually trying to perform this kind of slightly funny interpolation to this imaginary 3-sphere, then this large transformation, it becomes very naturally becoming kind of like the homotopy classes of mapping the gauge field over this 3-sphere. And in fact, what we can really do here is that we can just instead of doing the embedding on this x0, but we do this on the kind of loss this x3 coordinate, and then this perform the interpolation precisely at the when the other 3 embedding coordinate are equal to 0. So this is a kind of status for the ADS3 that if you are trying to perform this kind of naive complexification. So that's as far as we can say along the line of kind of purely kind of holography story in dealing with the ADS3 cases. Okay, so yeah, I mean, so here this is somewhat the kind of caveat or the one direction that we haven't explored as much as we would like for the time being. Okay, so we change your gear a little bit in sometime last year that to kind of study this kind of Euclidean path integral, this Einstein gravitational path integral using this mini-superspace approximation instead. So of course this is kind of going kind of almost away from the holography, that story that we had earlier. But there's some interesting phenomena we observe here, and some of them are consistent with the holography story that we described here earlier. So let me be a bit quicker here. So our starting point is the following Einstein-Hilbert action, which I mentioned a few times, but only kind of writing down now. So the boundary term here are basically the Gibbons-Hawking term which we need to regularize the action. And then we also have the contact term right here. And roughly speaking, the mini-superspace approximation, it boils down to making a very specific ansatz. And in this case, basically, you also assume the spherical symmetric. So the only non-trivial degree of freedom is actually kind of all encoding all this kind of radial coordinate and the time coordinate, which are parameterized by n tau and a tau. So, and we are focusing on the tau between 0 and 1. And then it turns out that there's actually a gauge redundancy which we could actually even set the time coordinate here, just reparametrization of time really, to itself to be a constant. So we can reduce the task of evaluating this whole gravitational path integral after substituting this ansatz into just trying to figure out two things. One is basically the value of A which you should sample, right? So you basically have to solve the classical equation of motion for A, and looking at the fluctuation around it, and then actually also figure out that the integration contour in this time coordinate n. So okay, so we do this in steps. So first, to find out what the A is actually quite simple, and the only remaining thing to specify is actually the boundary condition. So we did a few cases actually. So one obvious one is having Dirichlet on the both sides. So we assume again that universe started from nothing when tau equal to 0, and then go to some finite size later on. So in this case, when you impose a boundary condition, and the action is actually very simple. Actually, I pointed out it's just a simple harmonic oscillator, really. So the solution looks like this. And in order to properly evaluate the path integral, then we should also actually including all the one loop fluctuation around it, so we can compute it. So that gives some additional contribution which encoded in this 1 over sine n. So to work out the contour so this is basically the A part, the A evaluation part is done. And then to finish the calculation, then we actually also need to figure out the contour for n. So the way you can do it is actually we can first figure out where are the saddle point, given this action. Now n we can still move around. So we will try to find out the saddle point for n, and then trying to join all these saddle points. So we just basically work out what the dn by di by dn equal to 0, and there are multiple number of the solution. And this look like this. This is a complex n plane, and so all this saddle point labeled by this value actually, so you have a real and the additional imaginary part basically coming from the original action, and the n plus half pi is actually precisely coming from the one loop determinant given the following form. So what we see here, funny enough, is that there's actually a kind of a stock phenomenon actually happening. Or more precisely is that we see that basically the steep descent contour that kind of emanating from one saddle point in this red dot actually ended up at the other kind of red points. So and so on. So this actually makes the precise identification of an integration contour actually rather difficult. So we kind of draw our, so what do we do? So usually when we deal with this issue, then we try to deform the contour slightly to avoid all this additional saddle point which we don't want. So this place, I guess, is the only one we kind of, I wouldn't even call this like the holography, but more like we are drawing the inspiration of a holography because we could also interpreting, like earlier we saw this kind of relation between the central charge in the leading order and next order. But we can also try to interpret this as, trying to shifting our de Sitter radius. Now you kind of combine this 13 here with the de Sitter radius, and then you kind of shift it slightly off the real value to the imaginary value. And this actually corresponds to precisely what's needed to deform those contours. Of course, you still have two choices in general, like you can have a plus minus to actually avoid this. But in our choices here, we are dealing with a de Sitter, that we choose the positive sign, and then we basically correspond to like kind of moving off this first cases, the one on the left rather than this on the right. And finally, based on this deformational contour, what we need to do is then, because we can actually work out exactly the contribution to the saddle, the actual value of the action for each of those red dots. So if we want to actually reproduce, so we're kind of doing a mixture of holography and this how should I put it? This mini-superspace approximation. Now, if we want to really reproduce also the holography result then we will actually only have to pick out two saddle points, which correspond to this J plus minus half, sorry, J plus minus 1, and then this J0 minus. So the contour has to go from this all the way to here, and then we kind of going around this branch cut and taking up to infinity. So, and this is what we're trying to describe in this slides over here, that we will have to have appropriate saddles, and they become a combination of this all these three contour together, and one could actually draw this out, and basically that's what I was trying to describe earlier. And similar things, like actually the funny thing here is that, if you were trying to mess this up a bit, for example, have a Neumann boundary condition instead at the t equal to 0, and carry out exact analysis, then you realize that, for example, the saddle you had earlier, it turns out it's actually not a critical point, but rather it's a critical point, but not an extremum, but rather you have an inflection point. And actually, you're also missing the case when the saddle point at n equal to -1, now which you actually needed to reproduce a CFT result. So we kind of, I wouldn't want to oversell this. I mean, I wouldn't want to oversell this as what we did previously, that when we really have an explicit correspondence between the de Sitter space and the holography, but rather this is more like we are borrowing, because on the gravity side now we are really using this mini superspace approximation. Now we actually in general don't know how precisely how to correspond those with different kind of CFT observable. I will only say that we were aiming to reproduce a CFT. If we were aiming to reproduce the computational two-point correlation from the CFT, that this is what we have to do. This is a contour we have to do that for in the mini-superspace approximation. And yes, so similar thing when we did for the ADS cases, then what we see is that it's really just changing from all the sign coordinate to the sign function to sign instead, as you might imagine. Those are the saddles, and but instead I kind of rotated right from the 90-degree of this whole complex Z plane. And here we again have this similar kind of Stokes phenomenon, and we can perform the same kind of deformation we did earlier, just using the corresponding central charge and the alluvial coupling and so on. But here, that what we saw is that yes, we could avoid all this additional saddle point that we don't want it. But what's happening is that, actually more detail probably in our paper, is that nevertheless, the total contour in each cases, if we were trying to reproduce what we saw on the ADS analysis, that there we still have this kind of infinite number of saddle, then we have to include all of them. Then in this case, it's actually CFT would tell us that the contour should be used in using the kind of mini-superspace transformation to study the ADS3 in the case, should have just purely the kind of positive real axis in this case. Yeah, so I guess this is an example. Yeah, I'm slightly kind of agonistic about this part of analysis, that because we don't have a full, as you can see, that we don't have a full explicit holographic correspondence in this context. But if we were to go a bit cavalier about it and using CFT as result as a guidance, then at least this helps us to pick the contour, that if you were to do this via the mini-superspace approximation. So I think that's the kind of one-line conclusion from this game. Okay, so that's all I got to say, and sorry it's run slightly over time, like 15 minutes or so. So yeah, so that's the conclusion. I will just leave it here, really. I mean, so this talk, holography to explain complex geometry, and in principle we can do for other higher point functions, and in fact in our cases that this would actually correspond to kind of like network of the Chen-Simon Wilson line, that sometimes they even have interwinding things as well. And yes, so if you were trying to work a bit harder and study, actually the last point is probably more interesting. If you work a bit harder to study the higher spin cases, that can be done. And in fact, the explicit de Sitter higher spin CFT correspondence we also discussed in our earlier paper. But I guess being able to do what we did, it kind of hinge on availability of the correlation function of the TODA CFT and analytic continuation and so on. But once they become available, then it would be very nice to continue this direction and see what holography can help us. Yeah, I end my talk here. Thank you for your attention. Yeah.
Oh, thank you, Heng-Yu, for the nice talk, and it's wonderful explaining all the points. So let's ask the audience if they have any questions. Then
yeah. Mm-hmm.
in the meantime, so I wanted to ask, so when you're doing this mini-superspace, this thing, so what does this, so the range of any integration basically for n?
Mm-hmm.
So n as of now, basically, it was left unspecified. It seems like there is some reason to, which will be utilized later in order to put an actual value. What are the range of limits of integration for n?
I mean, do we set any upper bound for the n? Yeah, any range for the n? Yeah, we don't actually. I mean, n here, n in our ansatz is really just so for example, effectively by setting n to be constant, right? It's like we are almost setting basically like you can view this as by scaling n, we are kind of almost rescaling the time coordinate here. Yeah, so otherwise we don't have any restriction on the value of n. Just generally complex in our game. We're kind of making this is almost like kind of most the simplest non-trivial ansatz you can play this game, right? I mean, you're just assuming the spherical symmetry, right? Having the S2 sticking here, and then you have some radial. Radial part that's giving the expansion vector, so to speak, right? And then you have some. It's like almost it's kind of cosmic time, really, right? This is like telling you coordinate to the time, and you just have to specify all these things, like when you evaluate the integral, really. Yeah.
So is it also possible to map the results of Dirichlet to Neumann and vice versa, basically?
Match to what? Neumann or
Neumann and Dirichlet boundary conditions. So
suppose
that's
the case. That's the case we failed. Yeah. So basically, one side Neumann and one side at least if we were that's what I'm trying to make the point is that So if you were trying to match with suppose you were trying to what's the right way to say it? Suppose if you were trying to use instead of using Chen-Simon formulation, that's the right way to say it. Instead of using a Chen-Simon formulation, right? You're just basically starting with your path integral with Einstein gravity. Then this is what you would do, right? And then you aim to match with your CFT 2-point correlation function calculation. Then you realize that not all the boundary condition and not all the contour that allow you to do so. So in something like CFT give you a restriction. That what allow boundary condition and contour you can do.
I see.
In playing this game, but of course, I'm trying to make a disclaimer, and in fact, in our paper, we are also quite cautious about it. Here is that, it's basically we don't really have a, for example, I can't tell you, for example, now if you want to do, say, inserting 3-point function, 4-point function, what should be the natural starting point? In terms of ansatz, right? Never mind the final result. What's the good ansatz to start it with here? So that's why we were saying we're doing somewhat exploratory direction in this one. Because there's no reason for mini-superspace to be the right way to describe the kind of quote unquote quantum gravity in the de Sitter, in the 3-dimensional de Sitter case.
I see.
So it would be nice to it would be we have some words, but I mean I guess we haven't been able to make it very concrete in our paper. How we can make these things more more concrete, but this is something would be nice to. I think probably the same can be said about many of those using a mini-superspace and study there were paper, for example, by Neil Turok and Jean-Luc Lerner earlier, and more recently Masazumi Honda and all that, right? So, actually one thing interesting though, I see is that if you compare, so we talked to Masazumi about this stuff. So he was doing the same game for 4-dimension. So on the other hand, 4-dimension, you don't have this Stokes phenomenon appearing. That was actually kind of interesting in their so basically to do with so roughly speaking, what we had is to do with this power of one loop determinant. So this half depends on the space-time dimension. So in 4-dimension, this actually become kind of integer power. So we actually don't, for example, have this branch cut or this Stokes phenomenon we are observing over here as well. So in different dimensionality, that's also a different game. But of course, in 4-dimension, their problem is that we know even less about the CFT data.
Yes,
So we could actually purely play this game in the gravity. Yeah, so that's a caveat in that setting.
Yes, that's true.
Yeah. So it's a question of finding a sweet spot that we have enough on both sides.
Yeah, that is true. That is true.
Mm-hmm.
Let's see if they have chat
Yeah, I
box.
just
So there is.
want to have a
Yeah.
small question. Yeah.
Yeah, please.
So yeah, so actually I am not from high energy physics. I'm mostly from the modified gravity cosmology field. So I just wanted to
Okay.
ask about the basic stuff about the BTZ one. So when you are computing the BTZ black hole and in the DS3, I mean DCTA 3, I guess. So I am first
Okay.
asking like in the BTZ, what does it mean by it is embedding in a DCTA 3? Because it is already 2+1 dimension, I think you are taking, right? I mean, so there is already a cosmological constant to make sure that there is a horizon, right? I mean, otherwise, in 2+1
Oh yeah, so
dimension,
it just
ordinary.
meant I just meant like this is asymptotically to away from this singularities. Away from this is actually asymptotically to de Sitter space-time. That's all. That's all I meant. Yeah, it's
But
basically
that
the
would
same.
be
Like for
included in
example,
the definition of BTZ, right?
I guess
BTZ already comes with a cosmological constant, right?
Yes, that's right. Yeah.
Okay. So I'm
Yeah,
just
that's
asking
right.
that is this metric is same as what we do in 2+1 dimension, say black hole with a cosmological constant, or like is it just a coordinate
Yes.
transformation of this? Yeah.
Yes, in this case, this is it's a coordinate. Well, it's kind of orbifold, right? It's basically a BTZ black hole in ADS3 is an orbifold of the ADS3, right? So here, yeah, it's more like an orbifolding of the.
So quotiented by which group? Like, I mean, quotiented by like U1. I mean, because theta goes to theta plus 2 pi. Okay.
Yeah, that's right. That's all we are doing. Yeah.
I see. Because that's what. Oh, okay. Because it is a orbifold, there is a canonical point, right? Because otherwise, in BTZ black hole, there is no problem. Like, I mean, the metric doesn't look like this because there is a naked singularity, and you give a artificial horizon by the negative cosmological constant. I mean, in 2+1 dimension. So that's what I was little confused.
Yeah, sure. That's what we were doing. Sorry about it. Yeah, that should clarify.
No. That's fine. Okay. Thank you very much, sir. Overall, it's a nice talk. Thank you again. Sure.
Yeah, no, thank you much for your attention.
So let's see if there are no further questions, then maybe we can wrap up this thing. So thank you, Heng-Yu, for giving a very wonderful talk.
Pleasure, and hopefully we'll get. Yeah, hopefully,
yes.
like some of you are very interested in visiting us in Taiwan, and do drop us an email, and we can arrange it. Yeah.
Please do come also in Bangalore sometime. We'll be very happy to host
I'll be
you.
very happy to. Yeah, so we just advertising a little bit of our group. Then we now just in addition to me, and then we have a couple of Yuting Huang and also Jia Xiansheng working on the amplitude.
Yes.
And also we have a Pei Ming Ho, who is recently more interested in black hole information. But right now we also have a visiting professor from Hikaru Kawai. Yeah. He is now currently at the NTU visiting us.
I see.
And our group have about 5-6 postdocs usually, and we regularly have a kind of position opening in our group. Every year we always have 1 or 2 postdoc opening, and
I see.
And so yeah, and right now, Taiwan actually. Just kind of use this opportunity really. I mean, in Taiwan now we actually now have a more and more, especially in our department, that we have more and more Indian researchers in our department as well, and so hopefully we have a more. Yeah, I told Aninda before, so we should have more kind of collaboration, and hopefully we'll get more Indian researchers interested in
that would be wonderful. That would be wonderful.
Yeah. Okay, so hopefully to hear from you.
Thank you, Heng-Yu, for the nice talk. So I stopped
thank
the
you very much,
recording.
and hopefully.
So these recordings, we have a CHEP YouTube page where we upload it in the gauge gravity this thing. So by Monday I'll do the editing and upload it.
Yeah, okay. I will send her the slides if needed.
Okay, sure.
Do you need the slides? Yeah, okay. I'll email the slides then. Okay.
Yeah, sure.
All right. Okay. Thank you very much.
Oh, thank you.
So, take care. Thank you for your attention. Okay. Bye now.
Bye.